we up and running? Okay, awesome. Okay, so let me get started. You are hot.
Okay.
I didn't mean that in an inappropriate way. All right, good afternoon. Thank you so much for joining us, especially because I know it's the last day of classes, and if you're not sleep deprived, I don't know why. So thank you all for coming. This is our last talk of the Journey to the Sun series for this semester. It is not the last talk. We have ones planned for January, February, March, and April in the spring, but we're taking the month off because, hey, it's holidays. So I'd like to introduce our speaker. We're going to be talking about space weather today, so I'm super excited for this talk. Our speaker was kindly agreed to talk to us is Dr. Peggy Hill. Dr. Peggy Hill received her bachelor's degree in physics from the College of William and Mary in Virginia, and then she taught physics and physical science at the high school and junior high level for 9 years, which is super appreciated because we need good teachers. And then she returned to get her PhD, and she got her PhD here at Southern Illinois University, so yay! She studied condensed matter physics from the School of Physics and Applied Physics, and completed her PhD, and then joined the faculty of Southeast Missouri State University in 2000, where she taught physics and astronomy and science education. And she is no stranger to the sun and solar eclipses, because in 2017, she was the lead for one of the 2017 CATE teams that did eclipse. She was part of Team 40, which was one of 68 sites across the entire country that was collecting eclipse data to study the solar corona. And then for the 2024 eclipse, because that one was so much fun, she did it again, and she was one of the leads for the team that was based out of McLeansboro, Illinois, as part of the CATE 2024 project. And so she's going to share with us all about how the sun affects the world we live in.
Okay. Thank you. Can you hear me? Okay. I hope not to lose my voice. I haven't talked for a lecture class in quite some time. I'm retired now and get to do all the fun things, go down all these rabbit holes. And I had a lovely time putting this all together, and I could have worked on it for another 2 weeks, but what you see is what you get. So I think it will be loads of fun. It's something I'm really interested in and enjoy a lot. I've been following space weather for about 10 years. And when I get up in the morning, I get my daily feed from the Associated Press. I also flip over then and check the space weather every time. So we'll get started here by taking a look at the fact that the activity on the sun, the surface creates a type of weather called space weather, and solar storms can impact the technology that we rely on every day. You wonder, how in the world can you have weather in space? But these activities on the sun's surface then propagate through the solar system and then impinge on what we have here. Just as with the types of weather we have here on Earth, NOAA, the National Oceanic and Atmospheric Administration, and NASA will monitor what's going on in space. The National Weather Service keeps track of space weather too. And just like we have weather here on Earth, these administrations also will inform the stakeholders, people in technology, people on Earth, our space flight, communications people, of the status of the space weather, because it will affect us. If we look at this, what you'll notice is that we have an image here of the sun, and the things that happen on the sun. The sun the sun is a big ball of gas, and it's a plasma. So it's full of charged particles. It has magnetic fields. Just like the Earth has a magnetic field, the Earth's magnetic field is approximated by a bar magnet. The Sun also has a north-south magnetic field, but it also, because it is a ball of gas, it's a fluid, and it has local magnetic fields that are localized on the sunspots. And then as that sun rotates, these magnetic field lines can become tangled and interact. So when we look at this, we're going to talk about what is space weather and how does it affect us. Because space weather arises frequently from storms on the solar surface, these solar storms will produce strong magnetic fields that will go through space, and there will be particles that are emitted from the sun's surface that then sweep past the Earth. And you can take a look here. Oops, hang on. Where was I? There we go. I knew I could mess this thing up. You told me, she told me. This is a very simple one. And, you know, Corey, this is...
We'll put it somewhere lower.
Yeah. Try that. Okay. Hopefully that will not detract from what's going on here. One of the things that you can notice here is that also around the Earth, we have our magnetic field, which then deflects some of the particles and will tend to interact with the stellar magnetic field that is permeating space here. So you think, how can you have weather in space? Okay. How can you have weather in a vacuum? Because we generally think of the sun surrounded particles. Let's make it particles because most of it's a plasma that stream by. So it's much less dense. The second difference is, of course, as I just mentioned, that we have atoms and molecules here in the air. In space, most of the particles are ions. They are atoms from which one or many of the electrons have been stripped, so they have charges. It's charged positive and negative particles, and they stream by. Another difference that we have between the interstellar region or the space and here on Earth is that the weather here is dominated by the water cycle. Okay, so the water molecules in the air will come together, they'll condense into clouds. Those clouds will then precipitate and then return the water to the surface of the Earth. It goes back to the oceans, and then the whole process begins again. It evaporates and then goes back into the atmosphere. The weather in space is dominated by the creation, the movement, and the destruction of charged particles. And so there's a difference with that. So we'll talk a little bit about space weather, which is primarily characterized by several types of events. And this is the way NASA and NOAA and the National Weather Service look at these events. They classify them in basically three types of events. They have solar particle events, solar flares, and coronal mass ejections. And we're going to look at each one of them separately in a little more detail. But before we leave that, you might think about the sun having a magnetic field and the magnetic field lines emanating from the sun, and that as the sun undergoes nuclear fusion. The particles are emitted in a solar wind that just kind of radiate outwards. But we have to remember that the sun is rotating, and different areas on the sun emit particles of different speeds, depending on what's going on. If you're in a quiet part of the sun, the solar wind approximates about 400 kilometers per second. It moves fairly slowly. If you have an energetic particle event, if you have a coronal mass ejection, these particles can be emitted from the sun at speeds of 2,000 kilometers per second. And you can have this going on different parts of the sun, all at the same time. And as the sun rotates, this is like a slice through the equatorial plane. As the sun rotates, you'll see that for those particles that are moving more slowly, the 400 kilometer per second, the sun rotates around a lot as these are moving outwards. As for the part of the solar wind that moves fast, it doesn't curve quite as much. And so you can see that the particles and the field lines can become tangled even out in space, and there can be some really complex things going on with that. And as the thing rotates, as those particles are emitted from the sun, it's kind of like a water sprinkler, you know, it goes around and it spews out particles in this spiral form. We're going to go through the anatomy of a large solar energetic particle event. This could be, this is just a generic event. It includes a lot of things going on, so it's probably a really good way to go through here. Now, I know that the letters here are too small, or kind of small to see, but I want to walk through this with you because this really will give you an idea of what happens when you have a solar storm. So on the surface of the sun, you'll have a collection of sunspots, and sunspots are composed of positive and negative poles. They are places where the magnetic field lines poke through the surface of the sun. They generally come in pairs or a group where you have north and south poles. So you have kind of a loop of magnetic field out from the surface. These areas will then grow and change on the sun. Sometimes they evaporate, but they can grow. And that as they move across the sun, you'll see that they change shape, the magnetic fields intertwine, and they grow and store magnetic energy, much like you would store energy in a spring. And in an event called magnetic reconnection, these magnetic field lines realign, and they release that stored energy. This shock wave will accelerate charged particles to very high speeds as they go outward from that sunspot. It's also characterized by a flash of light, of electromagnetic radiation, mostly not in the visible range. Most of that emitted radiation, electromagnetic radiation called solar flare, is transmitted as X-rays and extreme ultraviolet. So you have to have a satellite or some instrument that will see in those ranges. These shock waves, as this storm or this emission goes outward, they will accelerate charged particles that can sweep things that are in the inner solar medium out and away from the sun. It actually can clear areas, and that will allow for later activity to be even more impressive sometimes. It will often eject an expanding cloud of coronal material called a coronal mass ejection, and that moves outward towards the Earth and outward to the planets. The flash of electromagnetic radiation that's emitted in a flare will reach the Earth in 8 minutes. So the satellites will detect it very quickly. This is then followed usually by the front of the shock wave, which is mainly accelerated electrons, and they will, not electrons, protons, accelerated protons, and this can produce what they call a solar energetic particle event. They can get to the Earth in an hour or two. The remainder of the material, as it expands out, comes out more slowly, and it can be many millions of tons of material. And this coronal mass ejection, the majority of the material, the particles, will arrive at the Earth between 1 and 4 days. And this is the material that frequently will cause a geomagnetic storm. Okay, and then geomagnetic storms, okay, it says it passes Earth 1 to 2, maybe it can be longer than that also. But that's the main form of a solar storm, and it can have some interesting events. Okay, a solar flare, as we talked about it before, this is let me see if I can get this to work here. And they glow due to the energy release there. But you see it as a bright area on the sun. The primary energy source here is the reconnection of magnetic field lines. And it's really interesting because when you start back, I don't know if I can put this back at the beginning and show you. I should be able to. Let me see if I can. Yeah, here we go. If you look at the area in here, you'll see loops. And I just want to run through the first part again because these things are loops right now, but you're going to see in this area some of these loops open up. Okay. There you go. This now is your open field lines. It once was connected, and then now it's an open field line. The radiation takes 8 minutes to reach the Earth, and then it may or may not also trigger a coronal mass ejection. Sometimes we get big particle events out of it, but a big flare does not mean necessarily a big coronal mass ejection. And this is what happens, okay? This is an image that shows the results of a solar flare, and this shows that the high-frequency radio waves are absorbed. The red area in here, the red zones, and you see this is over Antarctica for the most part now, the red zones show where high-frequency radio waves are absorbed or attenuated, and you can't communicate in that area. If you're an amateur radio operator, if you are ship to shore, if you are aviation, they all use high-frequency radio waves, so there's no communication over there. So I'm thinking about these stations in Antarctica where you have researchers, so you have a period where you probably can't communicate with them. And this one, it shows a big area in the over Antarctica, and that indicates that there is, it's probably summertime. The sun is the solar, not the summertime, it's wintertime here. summertime in Antarctica because the sun is shining on it. The blue area is called an anti-solar location. When that electromagnetic radiation hits the ionosphere, it ionizes a region of the ionosphere that generally will reflect radio waves, and it's used for communication. With that ionization, it prevents that communication. So the area, boats and things in this region may have some kinds of interruption in their communications. And then here, this is nighttime, and we are not affected because the sun is on the other side, and it's ionizing the other half of the ionosphere. Over time, the electromagnetic radiation can do that. Radio blackouts are also caused by those energetic protons that get there within an hour or so. And that can cause things to spread further. So later on, we'll see a little place where there's an evolution of what's going on there. Coronal mass ejections, these are what we're interested in because if we like auroras, as I do, and I totally, how many of you guys saw the one on May 10th? Yeah, I mean, I was just, it was amazing. The only other time I had this far south seen the aurora was back in November of 1991 when I drove home late at night from graduate school here. I drove home from running experiments in the physics department and got home in Cape Girardeau, Missouri, and parked my car and looked up in the sky and I said, something's on fire. And it turned out to be the aurora. It was absolutely fabulous. This one was better, I tell you that. Okay, so coronal mass ejections are that emission of great masses of material during one of these solar storms. They'll carry billions of tons of material outwards. I think I said millions, but billions and billions of tons of material outward from the sun at speeds as fast as hundreds or even thousands of kilometers per second. They contain particle radiation. And again, in contrast to flares, they're not particularly bright. One of the things I wanted to show you here with this is the coronagraph on the Solar Dynamics Observatory. And you can see this was November 21st. This was a solar flare. And you can, the little specks on here are the energetic protons that are hitting the camera, creating snow. What you can see is there's a coronal mass ejection here at the 2 p.m. Period of time. And for those of you who are not aware of what a coronagraph is, a coronagraph is an instrument that looks at the sun and it wants to see the area around the sun. So what it does is it has a disk. It's like holding your hand in front of the sun to block the sun so you can see what's around it. This white area is really the radius, that shows you where the sun is. But they have to block it more than that in order to protect the instruments. And they've got some stuff. They're going to launch a couple of satellites soon that are going to be produce an artificial eclipse. And they're going to maneuver these satellites so that they can block just the surface of the sun and actually observe closer to the surface than they can here with the instruments. But as you see, this one instrument, you see it expanding, but where is it going? This is a 3D world, and this is a 2D picture. And is it from the backside of the sun? If so, we're safe. We don't have the stuff coming towards us. Or is it headed towards us? Do we need to worry about it? And this is where putting together information from a number of different satellites actually is very helpful. You can get a three-dimensional idea of what's going on. So the coronagraph will take an image like this, they'll put it up and they'll say, well, there's a big CME and we'll get back with you. We don't know where it's going. Okay, we don't know where it's from. Sometimes they have a good idea because they look at the surface of the sun and they say this is an active region and we expect something, but they really can't be positive until they take a look at that information. Now, because the storms are related to sunspots, and the number of sunspots is related to the sun's 11-year solar cycle, we have to take a minute to look at this. This is an image of the sun with sunspots on it, and we can monitor the sunspot number. Every 11 years, the sun will go through a period of maximum number of sunspots to minimum number of sunspots. And they give sunspot numbers here, average. They do it generally for the month. Maybe not on this one, I'm not sure how that is. But you can see down here, this is historically the sunspot count. It's not perfect looking, it's up and down. They did not expect solar cycle 25 to be this big. This was the predicted peak of solar cycle 25. They actually believe it's not supposed to come until 2025, but they actually believe that we have hit solar max a little bit early here. And you can see it's way up above what they were expecting. So the activity is high, which is exciting for us when we want to look at things like this. Okay, so we expect more solar storms. It's not unusual that we had our May 10th event. However, solar storms can occur even during solar minimums. A big sunspot area or solar max just means we have more opportunity for a solar storm, but they can happen anytime. Okay? To recap here, basically, you have things that, or events that start on the sun, and this is a bunch of different things here. These influences propagate through the solar system to all of the planets, to the Earth, and even out to Mars. They have, NASA has a couple of probes there on Mars that are watching the sun and keep track of it. Here on Earth, we have our magnetic field. We're generally protected from a lot of the stuff that goes on in the interstellar or inner solar environment here. I don't know what the word is for that, but in between us and the sun. Okay, so we have aurora, we have geomagnetic storms, and we even have ground-induced currents. We're going to talk about those a little bit more too. But how does this space weather affect us here on Earth? Why should I care? There are quite a few impacts of space weather, and I'm going to start from the inside out. First off, these solar storms, geomagnetic storms, can affect the electric power grid. They can cause current surges, they can cause ground currents, they can overload our electric power systems, they can burn out transformers, all kinds of things. And the electric companies now are aware of this, and they take precautions to protect the power grids because it's so important. Everything we do runs on electricity. Backing up, though, a step, I should have mentioned the aurora first because that's probably the first place we ever realized that there were solar storms. I mean, I know we've watched the aurora since prehistoric times, but it wasn't until 1859 when Carrington was observing sunspots, and later on there was a huge geomagnetic storm that we actually saw the connection between what happens on the sun and what happens on the Earth. Can it really affect what's going on here? And the answer is yeah. Okay, communications, you've already seen high frequency radio waves, maritime traffic communications, Department of Defense and military communications are affected. Ham radio operators, FEMA works on high frequency communications. So you have a lot of issues there with these signals being interrupted. Aviation has a couple of different things. And not only the communications, a lot of our intercontinental flights, you'll have a polar flyover. And storms really focus there because at the poles, the magnetic field lines will enter and exit the Earth. And so as the charged particles from the sun come in, impinge upon the Earth's magnetic field, they'll follow those field lines and then be transported to the poles. So aviation, one thing, communications, but another thing, they actually monitor pilots that fly these transpolar routes because they can be prone to more energetic particle events, these protons, which can be very damaging to human health. And they will reroute, if you've got a large solar storm with protons, they'll reroute those polar flights. And that costs money. GPS, positioning, you wouldn't think about it, but now farmers use GPS to do their planting. And a lot of different groups or different stakeholders use GPS construction for finding the right location for things. And these GPS signals can be degraded, they can be, it can cause the GPS to give an incorrect position. So things can go awry there also. Satellites, a couple of things there. Those protons can cause bit flips in the computers of the satellites, causing data errors, causing communications errors or instrument errors. And also, again, communications, trying to get information back and forth. Human space exploration, this is a big thing too, particularly if you want to think about a trip to Mars. Okay, we've got the Earth's magnetic field, we've got the atmosphere to protect us from some of this stuff, but out in space, they will often restrict the external, these, I guess, spacewalks or missions with what they call extravehicular events or something. They'll restrict those during times of solar storms because that radiation can damage DNA and cause health hazards for human space exploration. We're going to have an issue when we get out there and go to Mars. They will actually communicate with people, the astronauts on the ISS, and then those that are up in space, tell them to, the ones on the ISS, they'll tell them to go to a safe room. There are areas on the ISS that are more heavily shielded than other locations. And so they do want those astronauts to then take shelter during certain times. So all kinds of things. Yeah, why should it matter to us? Historically, some historic impacts. This fascinated me. I was looking at some of this stuff. In 1972, back before many of you were born, there was a solar flare event that led to a significant geomagnetic storm. One of the major impacts was to disrupt AT&T's long-distance service, and that was a problem. But one of the things that I found mentioned was that it also caused detonation of several underwater mines, military mines, the Navy's mines, off the coast of Vietnam. And I don't know if you know the 72, that area, not a pretty picture. But that was caused by that geomagnetic storm. Ground currents actually caused magnetic fields that triggered their detonation. 1989, the famous Quebec power outage. Okay, so this outage occurred, I think 6 million people lost power for like 9 hours in Quebec. It melted transformers. So that was a big event. It was from 1989 that many of the power companies really began to look at what do we need to do to protect against some of these events. Recently, Starlink, 40 out of 49 of the Starlink satellites that were launched in 2022, SpaceX, they had a whole group, 40 of them were lost due to a geomagnetic storm. As they were deploying this radio blackout and some of the other effects, just dumped them out of the sky. There are a couple of things with satellites. Not only can it cause communication disruption, but also when you have these events, it kind of puffs up the Earth's atmosphere, this ionization. So where the space shuttle and the low Earth orbit is about 300 to 500 kilometers above the Earth's surface, there's not a lot of drag, and Hubble and the International Space Station, because the amount of drag there is enough to slow it down, for it not to then plummet back to Earth, they have to boost their orbit about 4 times a year during a quiet sun, because that drag will actually begin to bring them down. During one of these events, they may need boosting every 2 or 3 weeks. Okay, so when you've got an event that then expands the atmosphere and increases drag, then you're in big trouble there. The final thing here was a prediction or a supposition here. What would happen if we had those 2 hurricanes and we've lost a lot of power right in that swath down from up through Georgia and Tennessee and North Carolina? You've lost power due to 2 hurricanes. What if you also had a solar storm? You know, what do we have to worry about there? So we do know that it can cause a lot of havoc, and it can cost a lot of money. You know, $50 million for the loss of the Starlinks. That we need to predict, to be able to predict, just like the weather here. If there's a hurricane coming, a tornado possible, we want to be able to take actions and mitigate that, or at least protect ourselves. Can we do that with space weather? We have more and more technology now that is vulnerable to these space weather storms. So we go to the beginning. In order to predict, we need to know more about the sun and its behavior. We need to be able to observe. We need to know the warning signs. And this is a great image of NASA's heliophysics system observatory. And it's a fleet of satellites, tons of satellites, that are looking at the sun. One of the things I do want you to notice here, because we're going to look at some things in a little bit. Let me check it. Oh, okay. Is that we have SOHO, and we have the Solar Dynamics Observatory here. They are extended ops. They are here way longer than they should have been. And in fact, I think Soho is like one of my favorites. You really should actually go and check out Soho. Let me see if I can find a couple of things here. And we're going to go into it. It's amazing how much extra work we get out of these. Soho was launched in 1995, and it was designed to last for 2 years. If you see at the top, it's on its mission day 10,594, so it's here some 20 years later. It monitors the sun's surface, seismology, solar wind, the outer corona. It orbits at Lagrange point 1, which is in between the sun and the Earth, so it's there before, it will get information before it gets to Earth, and it always has a clear view of the sun. It's one of the, its claim to fame is that by doing its job, it's discovered about half of the comets that have been discovered on Earth. So that's kind of fun. One of these things here, the pictures that are taken by it, here you can clearly see an increase in solar activity from 97, 98, and 99 as the sun approached solar maximum in the year 2000. So that's kind of cool. I like Soho because it was designed to last for 2 years, and within 2 years or 3 years, it totally failed, and they had to totally recommission it. Then the gyroscopes on it, all 3 axes failed. Okay, Solar Dynamics Observatory, this is the one that gives us our daily sun pictures. They just had, I think it was, it's Harvard, one of the universities that keeps the records for this or takes the data and gives us our daily sun picture, it had a flood and the data servers were totally destroyed. So it will be 2025 before we get their solar pictures. However, amateurs, astronomers are filling in, and from all over the world we're getting pictures of the daily sun from amateurs around the world, which is cool. Here's a bunch of other things. GOES and POES. We have satellites that are geostationary. They're about 22,000 miles away, and they are geostationary, so they're positioned above a place on Earth, and they rotate once with the Earth. The POES are polar orbiters, and as the polar orbiters are very close, they're about the same height as the space shuttle would orbit, and their orbital period is about 90 minutes, and they look at the Earth in that region. We started with GOES 1 through 3. We're now up to 18 and 19. 19 is going to be looking at, it's going to be launched in 2025, and it's going to be looking at lightning. That's going to be its main mission. But these are our fleets. The space weather follow-on is going to be Solar Dynamics Observatory, because really they're beyond what they're supposed to be. These observations are monitored and assessed by the Space Weather Prediction Center, which takes all of these observations and then distills it. It provides you with the space weather conditions, 24-hour observed maximums. This was on November 22nd, and the latest observed, it was all quiet on the western front there. They take that, they're able to take the data, put it into one of these models in here, and spit out some forecasts of what they think's going on. You get a 3-day forecast, a 3-day geomagnetic forecast, all kinds of things. Then, if they need to, they will send out alerts, watches, and warnings to any of the stakeholders that may need information. This is what got me hooked to begin with, spaceweather.com. It's your one-stop shop, not only for solar information, but for a lot of stuff in the sky. They are very good at explaining what's going on. So I've learned a lot through there. This is my one big content-heavy slide here. And I want to just go through this very quickly with you. And we'll move on because I want to do one quick analysis here before we're done. The largest space weather events are caused when the sun experiences a giant magnetic eruption. The solar flare X-rays hit the Earth's ionosphere, causing a prompt loss of the ability to reflect these long-range radio waves. Following the X-ray flare, magnetic eruptions sometimes accelerate huge quantities of charged particles. If they impact the Earth's atmosphere, they trigger radiation storms. And so let's look at what the Space Weather Prediction Center does here. There are 3 basic types of storms predicted by, or classified by the Space Weather Prediction Center: radio blackouts, solar radiation storms, and geomagnetic storms. And the only thing that I wanted to mention here, if you look at this, for radio blackouts, they look at the X-ray intensity. Currently, we have had in the not too distant past, many X flares, X1, 2, 3, 4. We had an X9 at one point early on. For the proton storms, those energetic particles, they have a level here. It kind of reminds me of your tornado, EF4, EF5, that kind of thing, 5 number scale here. And this is a flux of protons that are above 10 MeV in energy. Those are dangerous. And then here, the geomagnetic storms, G1 through G5. The May 10th event was a G5. So we did have a big one there. You can take a look at some of the impacts. If you have a R3 impact, low frequency navigation signals are degraded for about an hour, these X1s. And they list all of these things. You can look them up. You can't really see what's going on here. But S5, 4, 3, we've only had a couple of these energetic particle events, these S1 or S2. They've been fairly minor. And then this is the one that I like. This is the one that I look at to see if I'm going to see an aurora. And as part of what they mention here, they show you aurora for our G5 in May may be seen as low as Florida and southern Texas. And we were getting pictures from all over the place. Blackouts, complete collapse of power grids. We didn't have that. I mean, we really did okay. I want to mention one thing, the Carrington event. This is a picture of the sun. I'm just going to go through here. Corey, I'm going to speed my way through. 2 minutes here. I'm going to relate what I've talked about here to our May 10th event. This is a picture of the sun on May 8th. The gray thing in there is the sketch made by Richard Carrington in 1859, when he first looked at sunspots. That was a much more dramatic event than this one. Carrington's event actually disrupted telegraphs all over the US and Europe, causing the telegraph machines to shock people. The operators were able to send messages from some of the flares. Began with multiple flares and CMEs on May 7th and 8th, and an X2.2 solar flare on May 9th, causing radio blackouts. You can see here's a radio, that's the anti-solar point. That's where the X-ray flare was. And then 9 hours later, the sun has moved, rotated over the Earth. You see the anti-solar, that's where the sun is still ionizing the ionosphere, but now look at this. You've got a blackout, total blackout, North and South Pole both. So that has evolved. Looking at the GOES X-ray, you can look at the data. This is from the Solar Dynamics Observatory. The solar image on the previous page was that one right there, and the radio blackout images came from this big spike right here. Solar magnetic events, they unleash several CMEs, and this is the CME from May 8th. You can see a change here in the solar wind. All of a sudden, the solar wind picks up in speed. And one of the things of a geomagnetic storm, the interplanetary magnetic field tips south. And that allows the external sun's field to interact with the Earth's field and funnel particles into the Earth. All right. Severe geomagnetic storm likely. This is what it looks like when the Space Weather Prediction Center gives you a warning or a watch. This is what it looks like when they say alert. Here it was a G4. You can see the auroral, the auroral oval. The sun's over, the sun is over us. This is during the day. This will rotate around at night. Possible technology effects. Infrastructure operators have been notified to take action. And there you go. This was it. This was the G5 condition for May 10th. And this is what our auroral oval looked like. You can see that well down in, you expect to see auroras down in here. Doesn't mean they're not going to be down lower, but that's what we would expect to see. So with that, let me one more slide. These were the impacts from that event. It crashed GPS systems used by some farmers, which stalled planting. It caused the ISS crew to take extra precautions to avoid radiation. They went into their safe room. The image of the aurora is above my house, which is kind of cool. And the frenzy of May 2024 storm was strong enough to affect the deep sea. There were currents down in the sea. And it caused a large mass migration of satellites, which was dangerous because they moved in the sky. NORAD didn't know where they were, and then to get them back in the proper location, you're shifting all of these satellites, and there's possibility of collision. So those were the last things. So thank you.
So we've got about 5 minutes if people have questions. Does anybody have a question they'd like to ask? Bring you the mic.
All right, so I'm going to be working on like power plants and substations like that. So how do solar storms really affect like substations, for example?
Well, what I would think about would be two different things. One is the magnetic field, fluctuations in the magnetic field, and that will occur. When you have fluctuations in magnets, and I kind of flipped over that. There was an image there that showed the voltages running that across the ground during that May 10th event. And those currents then can affect different devices. So all of that factors in there. There may be other things too. I mean, I'm just an amateur where it comes to this. Yeah.
Other questions? Oh. Sorry.
So the distorted oval you were showing, did I understand it right that the wider side tended to be on the nighttime side of the Earth?
Yes. Yes.
Why is that? Because it seems like it should be bombarded on the daytime side.
Well, the auroral oval is a color-coded map of where you would most likely see the aurora. I mean, certainly there's a lot of stuff going around all over the place, but that would be on the night side. The daylight side, would be washed out by the sun. So
it's not particle density.
no, it's just it's probability of where you're likely to see the aurora. Yeah, that's a good question. Sorry about that. I kind of flipped over that.
One more? Okay, I've got one for you. Coolest space weather thing you've ever seen?
Oh my gosh. One of the things that surprised me a lot when I showed you the coronagraph with the SOHO is, and I talked about the Solar Dynamics Observatory finding comets and stuff. I've actually saw a sun-grazing comet on one of those coronagraphs, which I thought, wow, this is really cool. And then sometimes on the coronagraphs you'll see a little star-like things. One of them, I think, was on there, it had Jupiter on one side and Venus on the other.
Very cool.
So, I don't know.
It's very cool.
I am continually amazed.
All right, I want to thank you all for coming. Could we please thank our speaker one more time? Couple quick reminders. Our next talk will be the last Friday in January. We're taking December off. I mean, we're doing one early in December, but then it's the holidays. Also, for those of you that are watching solar-related events, remember Christmas Eve is Parker Solar Probe's closest approach to the sun. Yes. So keep your eye out on the NASA websites. There's going to be a lot of cool stuff coming out. All right. Thank you for coming. Have an amazing holidays.
Yeah.